Welcome to our mini section of the rotational motion unit on rolling. Rolling, again, just kind of like rotational dynamics, is combining some things that you've already learned about and just taking certain situations to the next level in terms of comprehension and sophistication. So we're going to, again, be mixing a lot of forces and energy in this particular topic. And I hope that this is interesting because it is one of my favorite topics to talk about. So when we talk about an object rolling, such as this tennis ball rolling over my paper right now, what does that really mean? Most of the time, when we talk about rolling, we're going to be talking about rolling without slipping. And what that means is that the contact point between the object and the surface is momentarily stationary. In other words, when this tennis ball rolls over, there's ideally one point of contact between the ball and the surface. And the idea is that as the object rolls, the contact point, so whatever part of the ball is in contact with the ground right now, is actually not in motion. It's actually not moving. Simply what happens is it gets put down and then it gets picked back up. That contact point, there is no sliding along the ground or there, between the contact point of the ball and the surface. So the other, if you're saying, okay, well, what does rolling with slipping look like? That would look like this, where the ball might be translating, moving forward, but you can tell that the ball is doing more rotating than it should for how far it's moving, and you can even hear, possibly, I don't know if you can hear it on this video, you can hear the slipping along the surface. I guess the other situation would be, instead of rolling with slipping, you could have rolling with skidding, which is kind of the opposite. It's where the ball kind of skids and then it might roll forward a little bit and then it skids some more, so the object is sliding forward over the surface, as opposed to rolling with slipping, the object is kind of sliding almost backward compared to the surface a little bit too much. Okay? Anyways, with rolling, this is also called like rolling smoothly. When an object is rolling smoothly without slipping, then the object has both translational and rotational kinetic energy. Okay? Now, let's talk a little bit about the energy in rolling versus sliding, because obviously when an object simply slides and it's not rotating, it only has translational kinetic energy. So for a sliding object, the kinetic energy is given by this, 1/2 mv squared. All the kinetic energy goes into translation, getting the object from one point to the next. So the object moves fast. Okay? It is speedy. It gets from point A to point B very, very quickly. Now for a rolling object, that's much different. For a rolling object, we have the kinetic energy being equal to both the translational component plus the rotational component. Remember, the equation for rotational kinetic energy is 1/2 I omega squared. Now, I want you to recall a couple of things here. First, I want you to recall that the relationship for objects that roll without slipping, we can say that the equation V equals R omega is true. Matter of fact, it's only true for objects that roll, in this case roll, without slipping. Okay, V equals R omega. The linear velocity is equal to the linear speed is equal to the angular speed multiplied by the radius. That's actually not true if the object is either skidding or slipping. So we can, so I'm going to hold on to that for a second, and I want you to also recall that I is equal to, what I'm going to say is B times mr squared, where B is some coefficient. For any object that you encounter, the moment of inertia or the rotational inertia will be some variation of this formula. It'll just change what B is m is the mass of the object, and r is some measurement that has to do with the shape of it. Usually it's a radius or maybe a side length or something like that, the length of some rod, something along those lines. So I'm going to rewrite this equation a little bit, and you'll see why in just a second. We're going to be able to compare the kinetic energy of a rolling object to the kinetic energy of a sliding object. So I still have 1/2 mv squared plus 1/2, I'm going to write b m r squared omega squared. Now notice I have an r squared times an omega squared. That would be like if I squared both of these, both sides of this equation, I'd have v squared equals r squared times omega squared. So I would have 1/2 mv squared plus 1/2 b m v squared. Notice that there's only one difference between these two, just the addition of a b in this term. So what I'm going to do is I'm going to pull out the 1/2 mv squared, and what I'm left with is this, 1/2 mv squared 1 plus b. So that is kind of interesting. What this shows you is that it takes more energy for the object to roll at a certain speed than slide. Now, why is that the case? For a sliding object, it's all translational. It's 1/2 mv squared. For a rolling object, we've reduced it down to 1/2 mv squared times 1 plus b. b is a coefficient that depends on the shape, but it's always positive. No matter what, b could be 0.00001. It's still going to be positive. Okay, and this term will be bigger than this term given the same v. On the other hand, if the kinetic energy is the same, the rolling object is slower. Okay? If we have the same k for both of these, then because this term is bigger, this term is a multiplier that's going to make, this is a multiplier that's bigger than anything over here, that's going to make the v for rolling smaller than the v for sliding. Okay, because you have this extra term getting multiplied over here, that's got to be greater than 1. So if the kinetic energy is the same, the rolling object must go slower, because what's happening is energy is taken from the translational kinetic energy and given to the rotational kinetic energy. Okay, so that's an interesting fact, and I wouldn't have assumed that before doing the math and proving this. Okay, I wouldn't have said that a rolling object necessarily moves slower than a sliding object, if everything else is the same. I wouldn't have guessed that. I want to talk really quick before we get to our example about how friction plays a role, and just a little tiny bit about slipping and skidding, or spinning and skidding. But let's start with friction. Okay, we're going to imagine an object spinning on a surface with friction. Okay, so let's say we have our object here. Okay, and it is rotating this way. All right, and it's on, I know I kind of drew this wrong, but it's at contact just at one point right here. Imagine it's like, for instance, like a tire. Okay, so the tire is being turned by some internal torque from the engine. So let's say that this thing is already rotating. Let's imagine friction's kind of got some weird rules to it, and what I think really helps a lot of times is to imagine what would happen if there was no friction. So if there was no friction and this object was being made to rotate like this, then this point that's in contact right down here would simply, relative to the surface, just be moving to the left. Okay, and if there was no friction, that would be fine. There's no force between There's no resistive force between the surface and the tire to slow that motion down. Okay, so without any friction, that point has no trouble slipping to the left. It would move to the left relative to the road surface. Since there is friction, however, friction tends to oppose the motion that would happen if friction didn't exist. So if the point in contact with the surface would tend to slip to the left, what that means is that friction must act to the right. So if this is a car tire, the force of friction actually points forward, which is very interesting. Okay? So even though another force causes any initial rotation, if there is no force of friction, this rotation would not move the car. That's because there's no force driving it forward. If there's no friction between this point and the ground, if there's no friction there, then that point is free to move to the left. There's no frictional force to the right. If there is friction, on the other hand, then you get a frictional force to the right, which is kind of counterintuitive because we usually think of friction as opposing the motion of any object. What it really does, the rules are kind of complicated. It's very situation dependent. It opposes, I guess I would call, local motion of an object, and that's one of the better ways I've thought of to try and think of it. And it's probably still not 100% right. So we have an object spinning on a surface with friction. The point of contact between the object and the ground I don't know why I have parentheses there, would move left relative to the ground. Therefore, since there's friction, the ground places FF to the right. It's actually friction that propels the car forward. If no friction, there would be no forward motion, and all you would get is the tires just spin. Okay? So friction plays a very interesting role with rolling. You can't have something roll without friction. If there's no friction, this object will just spin in place. It could slide without rolling back and forth. And as a matter of fact, if it was spinning and then someone pushed it like this, it would continue to spin as it moved forward, but that's not true rolling. Rolling means that you have this condition where V equals R omega, and that's not true unless something is truly rolling, unless this point on the ground is not moving when it touches the ground relative to the road surface. Okay, so that's a very tricky situation, and it's a completely true scenario. Cars move because there is friction between them and the ground. If there was no friction, those cars would not move. I want to talk very briefly before ending the video about slipping, both spinning and skidding, and I mentioned them before. Okay, so for a smoothly rolling object like we've been talking about, you have this condition, A equals alpha R, or in other words, the linear acceleration, if there is one, and this I think applies to the speed relationship that we talked about earlier. The linear acceleration is equal to the angular acceleration multiplied by R. Now, that happens because of friction. All of rolling, that was the point of this this first part, all of rolling happens because of friction. Without friction, there can be no rolling, okay? What if there's not enough friction? What if there is friction, but it's not enough to cause the object to not kind of slip a little bit as this goes? If there's not enough friction, object, I'm putting in quotes, spins too much. It rotates more than it translates, okay? It rotates more than it should, given how much it's translating. And what happens there is that the acceleration is actually less than alpha times r. The angular acceleration, the rate at which the spinning is speeding up, times the radius is greater than the linear acceleration. I'm just going to put in parentheses, it doesn't move as far as it should. Okay, so that's one thing if there's not enough friction. What about, on the other hand, you've seen sometimes when you hit the cue ball in a game of pool, you'll see it slide over, okay, the surface, and then it kind of starts rolling, right? Or if you you can do it with like a ping pong ball. If you have it on your finger and you backspin it, it'll kind of skid and then it'll start rolling possibly. If the linear speed is too fast initially to allow that friction to catch on and have it roll, then the object skids. Imagine you're trying to hit the brakes in your car and you're moving forward, and you're still moving forward, the tires are rotating a little bit, but they're skidding more than they rotate. Instead of rolling smoothly like this, or instead of kind of over rotating and slipping like this, the tires skid. It's still rotating, but there's more skidding going on. It slides too much. And that happens when your linear acceleration is greater than the product of your angular acceleration multiplied by the radius. Okay, so that's not a particularly big part of this topic, but I did want to mention it just in case that it comes up somewhere. But you can start to see that rolling is pretty complex. We're going to do an example in the next video where we see why rolling or we're going to do the math behind rolling. But what I want you to take away from this is that number one, for rolling, you don't have any relative motion at the point of contact between the object that's rolling and the surface. Rolling objects tend to move slower than sliding objects because some of that energy has to be transferred to rotational kinetic energy as opposed to translational kinetic energy, and rolling would not be possible if not for friction. Friction is the force that allows rolling to occur. Without friction, there can be no rolling. Okay? I'm going to stop there, and we'll do a nice example on the next video.